Now, let's suppose we don't even have a function to work with. Well, that's going to lead us to section 8.8, numerical integration. You've started this a little bit in chapter 1, in Calc 1, when you were introduced to integration with this idea of Riemann sums. Because remember, an integral, why do we often need to find an integral in an application? Is to get an area under a curve. And an area under curve between two distinct points, if you recall, can be found using, let's have our x. Suppose I just want to go from 0 to, x1, x2, 3, 4. So when you were introduced to integration, you learned something called Riemann sums. And the idea behind these Riemann sums is you draw a bunch of rectangles under your curve. And if you get the area of those rectangles, you can then estimate the area under the curve. So suppose I wanted to get the area, let's go from x1 out to x5. I can start at x1 and draw rectangles. And there were different ways we drew the rectangles. We drew them like this. These were called our left-hand Riemann sums because it was the left side of every rectangle, right, that touched the curve. And then you learned, well, the issue was you're only going to get the area, you're going to have all this error, right? We did left hand, if you recall, you did right hand Riemann sums, remember that? We're going x1. In the right-hand Riemann sum, it was the right side of every triangle that touched the curve. So you start all the way to the right and then move over. Hold on a second. And you're right. There you go. So then, here's rectangle 1. The right side is touching the curve. These are right hand, and you still had error. We overestimate it with this one. Okay, so this is just a quick little review from Calc 1. And then we did something called our midpoint Riemann sums, which were, of course, a little bit better. Because with the midpoint, right, you still have x1, 2, 3, 4. But what we said is let the middle, so you have a little bit over and a little bit under, right? So then you draw, let the middle, a little bit over, a little bit under, and you draw these rectangles. But the middle touches the actual curve, a little bit over, a little bit under. And the idea here was you have a better estimate because the area that's outside will kind of balance the error that ends up inside. And you get a more accurate estimate, but these are still estimates. All right. Now, let's look at the midpoint one for a second. Or any of these. You also found that, if you take the limit of the number of triangles as n goes to infinity, and these triangles get smaller and smaller and smaller and smaller, you end up with less and less error to the point, if you take it to infinity, that becomes your integral. So remember, the limit of all these summations as n goes to infinity of summing all these rectangles, and these rectangles kind of end up being, you know, your f of x, delta x, and we'll talk about the f of x. What f of x, we'll call it f of x of I. Where that comes from depends on whether you're using right side, left side, or middle. That x of I is a different value, but either way, the f of x of I is the length of your triangle, the delta x is the width. You sum all these areas together, because area is length times width, and you get your integral, right? You get your integral, and that's where integration actually comes from, and you get an accurate area under the curve. But here's the thing. In order for this to work and to use an integral, you need a function, right? Well, in the real world, when you're collecting data to get these data points, you can't always have a function. You know, the real world doesn't spit out a function. You collect data and say, hey, sometimes data does fit a function real nice. You can find lines of best fit or curves of best fit. We do this in statistics with regression analysis. You take a bunch of data points and you try to fit it to the best function you can. You're still going to have error, but that's one way of doing it. Another way is just to use your discrete data points. And if you only have these discrete data points, you have to do what we call numerical integration. There's no function for you to do the actual integration in. So you just have to calculate it using summations of these rectangles or other objects that you'll see in a minute. You're thinking, well, I'm never going to have to do that. Well, that's not true. A lot of students in this course are engineering students. When you go off to your next class, you take, for example, my son is over at Rutgers right now. Left RVCC, went to Rutgers, was in his fluid mechanics class last semester. He had to do a lab. The lab was, they had to collect a whole bunch of data to find the pressure difference behind a cylinder in an air tunnel. He had a lot of data points at exact intervals. And they had to find the area under the curve that was created, but there was no function for this curve. So the professor goes, well, you're going to use numerical integration using a trapezoid rule. Well, we'll get to the trapezoid rule today. So that was a clear example of having to apply numerical integration. Not always, it's a bit tedious. So usually if you have 100 discrete data points, you're not going to do 100 calculations. You set up a computer program to do this for you. But the Riemann sum and the way you learned what an integral was in the first place is what really is the concept behind getting doing numerical integration. So your midpoint approximation for our rectangles, right? You have n number of rectangles. We don't have a function, but we have, right, whatever it happens to be. So we would start, I need the midpoint between x sub 1 plus x sub 0. So what's that? Oh, that's x sub 0 plus x sub 1 divided by 2. That's how you get the midpoint times whatever delta x is. There's delta x is the difference between them. And then your next one would have to be, well, now I'm going to take x sub 1 plus x sub 2 divided by 2 times delta x. You should always have the same delta x. So in other words, your x values should always be the same distance apart. It makes it much easier. And this can continue up to x sub n. This summation would continue. And then you'd have, you know, x sub n minus 1 plus x sub n divided by 2 delta x. And of course, you can pull your delta x out of that function. That would be, you can pull that out and just have delta x parenthesis times each of the f x values, because these f of x values, right, this is going to be this height, right? This is f of x plus 1, x plus 0, sorry, x plus 1 divided by 2. You want this distance, all right? And of course, all of this does create error. If you know the error, if you know the actual numerical solution, right? Suppose you know that and you have an approximation. Suppose you have a numerical solution is C. Now, of course, if you have an actual solution, you wouldn't do a numerical solution, but often what you do is try to, the exact solution is not always known. So the goal in practice is to estimate the maximum size of your error. So absolute error is going to be the absolute value of C minus X. So it's just the difference between what you got using your numerical estimation versus what the actual answer is. And a relative error is going to be that value, that difference but if you divide by the actual, then you get a percent. Relative is can usually be written as a percent. It just gives more information when you do a relative error versus an absolute error. You may recall from Calc 1, many of you did a lab with Riemann sums and you calculated errors, so you kind of already did that. There's no, you're just honestly just applying the midpoint rule. There's nothing, I know, if you're asked to do the midpoint rule without a computer program to run it 100 times with 100 discrete values, you can be given and told, for example, approximate the integral from 2 to 4 of x squared dx. Now, I know you can calculate that, but if you were asked to approximate it, it's kind of best to draw it out. So our parabola, I'm going to kind of go like this and draw it like that to make it easier. And if we're going to go from 2 to 4, let's put 2 here, 3, 4, right? And let me get you some more information. In MATLAB, you might get a problem where you're asked to approximate it using midpoint rule. And you'll be told how many n intervals to do. So let's do n equals 4. So that means I want to draw n rectangles, and if you recall, you would do b minus a divided by n, so 4 minus 2 divided by 4 is just quick review from Calc 1, so you get 0.5 or half. right? So each n interval has a delta x 0.5. So that makes sense. So when you come over to your curve, the first one, we're using midpoint. So I'm going to need 1, 2, 3, 4 rectangles. For the midpoint, I got to go in between, right? I didn't mean to do that. I want to change that color right there. There we go. All right. Midpoint's here. So the next one's going to go here. And there's my 4 rectangles. With my midpoints being here, 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 and here. Your midpoints are your x sub I values. So let's calculate. Midpoint 1 is between 2 and 2.5. So it's 2.25, right? Midpoint 2 is between 2.5 and 3, 2.75. Midpoint 3 is 3.25. And midpoint 4 is 3.75. So there's your midpoints. So to do M4, call f of x, of course, is x squared. It would be delta x, we'll pull that out, times (2.25 squared plus 2.75 squared plus 3.25 squared. And if you do all that, you get 18.625. We can quickly calculate the exact area by just taking, all right, so this is a numerical estimation right there. Of course, your exact is just, you can calculate your integral of x squared dx, right? X cubed over 3 from 4 to 2. That actually comes out to 56/3. So I get an absolute error. I'm not estimating 56/3 because it would be irrational. All right, and then of course, relative error is that 0.0417 divided by 56/3. And this is often, these are estimates, of course. This is often written as a percent, so be 0.22. So your relative error is way less than 1%. Again, you would never use, this is just showing you how, but you would never use this if you had an actual integral, if you had an actual function. All right, so let's talk about other numerical integrals. So one of them is called the trapezoid rule. So again, suppose you just collected a whole bunch of data. I'm not going to do, but you had like 100 data points. I'll just do a handful of data points. And, you know, your data points kind of go like that. I don't know. And there's no function you could fit around those data points. I mean, you can estimate a function. Sure, I can go, oh, it's something like this, right? All right. And I'm going to go from, right, x sub O. And let's suppose, unlike in my drawing, they are all perfectly, the intervals are exactly the same. Okay, let's suppose the intervals are exactly the same. They look pretty close. Some of them do. Maybe not all of them. So another idea is, instead of using the midpoint rule, which again kind of creates these, you have a little error on either side, there's an idea that if I draw a rectangle, we'll just pick 2 of the values here, right? So let me make a better curve. Let me see if I can do it in blue. Well, no, we'll do it in black. Let me see if I can make a little bit of a better curve here, right? All right, so we got these discrete data points. I said, okay, I'm going to pick 2 of them. And instead of going in the middle, we're going to have a bunch of extra here, right? Right, have extra here and there. Instead of doing that, or have some over, some under, I'm going to try to get as close to the curve as possible. So how does a trapezoid get us as close to the curve as possible? Well, think about it. A trapezoid can be drawn with unequal bases. So base 1, base 2, and then connecting these 2. So we can draw trapezoids along this entire path, right? Boom. They don't have to be rectangles. When you do numerical approximations, these trapezoids actually work pretty well. All right? And this is the problem my son had to do. He had to put a whole bunch of, he had all the data points. They had 100, I think he had a couple hundred data points. They were all equal delta x's. So then he had to just come up with what the formula would be to sum them together. Well, all right, to do that, we need the area, not of a rectangle, but of a trapezoid. So in our Riemann sums, it was always f of x times delta x, because the area of a rectangle is just length times width. F of x was the length, delta x was the width. Well, what's the area of a trapezoid? Area of a trapezoid is 1/2, right? Sorry, my pen stopped. So you might recall area of a trapezoid, 1/2 the height, base 1, base 2. So if I take one of these trapezoids and put it on its side, right? There's my height, base 1, base 2. Okay? So this is now my delta x, right? Right? And then your B1, your first, well, that's like f of x sub 0, and that's f of x sub 1. So we turned it on its side. So, you know, this is B1, and that's B2. Well, let's start to write that out to see what it kind of looks like, right? And we could have n number right now. Well, my first trapezoid, this is trapezoid 1, right here, okay? First trapezoid, right? It doesn't want to draw the 1 for me. There we go. Trapezoid 1 is 1/2 delta x f of x sub 0 plus f of x sub 1. Okay, trapezoid number 2. 1/2 delta x. This now has, that is an x sub 1. Sorry about that. Yeah, 0, 1, 2, 3, 4, 5, 6, 7. I'm good. F of x sub 1 plus f of x sub 2. So this is trapezoid 1, trapezoid 2. Let's put trapezoid 3 in there. We're not going to do all of them. 1/2 delta x f of x of 2 plus f of x of 3 and dot, 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 all the way up to n. All right. Well, if I work that out, take a look at what happens. You're not going to have to do all this. I'm going to show you. I'm distributing my 1/2 delta x. There, I distribute it for trapezoid 1. Now I'm going to distribute it for trapezoid 2. All right. So there's trapezoid 1. There's trapezoid 2. Let's put out part of trapezoid 3. Hopefully you'll start to see what's happening here. So trapezoid 3 is 2 and 3. We're going to run out of space, dot, dot, dot. Because look, notice 1/2 delta x of the initial value. Can't do anything with that. Cannot do anything with that. We're just going to say delta x times f of x of the initial value over 2. That one is what it is. But look what happens to every pair after that. I have a 1/2 delta x of f of x of 1, 1/2 delta x f of x of 1. When you add two halves together, we get just delta x times f of x of 1. They come together to make 1. The next pair come together to make 1 delta x f of x of 2. That is going to continue happening. We're going to have, it's going to continue to happen until you get to your last value. In this example, there's only going to be 1. Okay, if we went up to n, you would just stop at n. So you're going to continue to bring them together, these pairs. I'm going to have to, maybe I'll shrink it a little. There we go. I'll make it smaller so I can fit it all. This will work. Right? Plus delta x f of x of 5. I still can't fit it all. I'll finish it down here. Plus delta x, f of x of 6. Now, when you get to that last value, there's no number after x sub 7 to match it with, so then you will end up with a 1/2 delta x f of x of 7. So what happens is the initial and the last have the 1/2. None of the other ones have the 1/2 in it. So I did this to 7, but the general formula for t of n, I'm going to pull the delta x's out now, is f of x sub 0 over 2 plus a full f of x of 1, a full f of x of 2, dot, 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 f of x of n minus 1 is a full, but when you get to that last value, f of x of n, whatever the n happens to be, in this example it was a 7, you're dividing by 2 again. That's how the trapezoidal rule works. So you would create, if you have a large number of discrete data points, you can create a program that lets you take your data points, take the value, so whatever, maybe your data points, your independent variables time, and you did it at time 1 second, at 2 second, at 3 second, at 4 second, at 5 second, and so on and so on and so on, and you have at 1 second it was, you know, whatever, the length or the pressure, you have an f of x value for each of them. As long as the initial one you cut in half and the final one you cut in half, everything else just gets added together. That is how your trapezoidal rule works. So we can try it real quick for a simple integral. Let's do the integral e to the x squared dx. Okay, and let's go from 1 to 5. And we'll do just n equals 4. So my delta x is still going to be 5 minus 1 over 4 equals 1. All right, delta x is just 1. So I made this kind of easy to calculate. All right, so I'm going to have an initial value to do t of 4, right? My delta x is just 1. So I need f of x. What's my initial value? I'm starting at, you know, think of it as we're going from 1 to 5, right? 2, 3, 4. So that's x sub 0. Two, 3, 4. So if your boundary goes from 1 to 5, your x sub 0 is your initial value of 1, and your x sub n, in this case 4, is my last value of 5. All right, my function is e to the x squared. So my delta is 1. My function, my first value is a 1. So e to the 1 squared is just 1. But that one I got to take over 2. I add that to f of x sub 1, which is, see that? That's actually a 2. Two squared is e to the 4th. X sub 3 is just 3 squared is e to the 9th. Plus e to the 16th. Plus e to the 25th divided by 2. And, you know, you can actually plug that into a calculator and get an answer. So they are all values. It's going to be pretty big because you're doing like e to the 25th. So you're taking 2 point something to the 25th power. It's going to be pretty big. But you can actually plug that in and get an answer. Your computer that you would plug this into would spit out an estimate. So there's a last one. That allows you to take discrete data points like we did before. You know, so I have these data points, but instead of using trapezoids, it actually allows you to use curves, which, as you can imagine, will get you an even closer estimate. So you can use small curves in between each data point. This one is called the Simpson's rule. We are not going to derive the Simpson's rule. It kind of uses the idea of putting mini parabolas between your points. But again, I'm not going to derive it. If you want to see it worked out fully, you can look in the text on pages 574 to 575. They do it in about a page, and 576. Yeah, you can look on those pages if you kind of want to see it worked out. I'm just going to give you the rule, and it's applied the same way the trapezoidal rule is applied. It's just a different formula. You will not need to use the Simpson's rule on the test, but you will, sorry about that, you will need to use it maybe doing a math lab problem. If you apply these parabolas and go through seeing how the Simpson rule evolves, you actually end up with your delta x over 3 times your initial value plus 4 times your next value. Oh, x of 1, sorry. And you alternate plus 2 times f of x sub 2 plus 4 times f of x sub 3 and it goes on and on until you get to, you end with a 4 times f, because you started with a 4, n minus 1, and you end with f of x sub n. So how do I know it's going to end up so even like that? Because Simpson rule is only going to work when n is an even integer. Simpson rule is not going to work on a non-value. So this one, which you want to note, is your first and last end up just the value of the function, or your independent answer. And then it goes, the second one is times 4, and the second to the last is times 4, and then it's always alternating in between 2, 4, 2, 4, 2, 4, 2, 4, 2, 4. Because we have an even number, we end up with 4, and then the final n. So that's the Simpson rule technically. Not going to do an example. You would fill it out exactly the same way you fill out the trapezoid rule. You just use this formula as opposed to the trapezoid rule, which was the initial and final values get divided by 2 and everything else is just not multiplied or divided by anything. This one is the initial and the last are left on their own, but then you alternate with times 4 times 2 times 4 times 2. You end up with 4 times the second to the last value. And then, of course, your delta x is divided by 3. So if you're interested in where all that comes from, I'll leave it to you to explore that section of your textbook, but we don't need to do that. So just practice some of the math problems in Math Lab. This is not on a lab, and it's not, on the test I might give you a small trapezoidal problem to work out for numerical integration. Again, you will come across this though, so you may need to revert back to these formulas, either the Simpson rule formula or the trapezoidal formula.